All right, so we're going to start talking now about slightly more complicated circuits. I know we've done that with our voltage and current rules, but what we're going to look at is just a full circuit analysis for circuits that are either series circuits or parallel circuits. Now, you got an introduction to both of these during the complex circuits lab. We made a number of series circuits, we made a number of parallel circuits, but we're going to start talking about voltage, current, but also how resistance works in all of these circuits. So just as a quick refresher, in a series, the resistors are connected one after another, and the key is the electrons must pass through both or all the resistors in the series. That's what it means for something to be connected in series. Whereas a parallel circuit, the circuit is connected so that the circuit splits and the electrons either pass through one resistor or the other. They don't pass through both. One quick note here, we're going to use this phrase connected in parallel. I just want to mention real quick that connected in parallel does not necessarily mean the geometric parallel where the two lines are parallel to each other. It's just this idea that there's two different pathways or two different branches, and the circuit splits. You can go one way or the other and come back together, but if the resistors are not geometrically parallel to each other, that doesn't mean it's not connected in parallel. So here we see two examples, and again, and you saw this some in the lab as well, but we have a series circuit here, so you see the physical layout of it. The current comes from the battery, goes through light bulb 1, goes through light bulb 2, and returns. This would be the circuit diagram of it. Here's your battery. This particular one shows 1, 2, 3 cells, but that doesn't really matter. Just any number of these symbols is a battery. And then we have our two resistors here, which in this case happen to be light bulbs, but they could be something else. Here is our parallel circuit, and we see that the electrons leave the circuit and they can either go through this near light bulb before coming back, or they can take this longer loop around and return to the battery. So we have two possible pathways. Same thing on our circuit diagram. We can take the inner loop or the outer loop. So at this point right here, the circuit splits, and then it comes back together right here, and that's what it means for it to be in parallel. We can either go through this one or this one. Let's talk conceptually about how current, voltage, and resistance work in a resistor. So the first thing is, in series, resistors combine to create more resistance. All right, so as we add additional resistors, it increases the total resistance of our circuit. Current is the same through each resistor, and that's because we have no junction. So the current that leaves the battery, which in this case is 3 amps, goes through this resistor, and this resistor before coming back around. They all get 3 amps as we see. Voltage is going to be split amongst the resistors, and it's going to add up to the voltage of the battery. That's because we have one single loop here, so the 10 volts of the battery is split. So we have 4 volts, 1 volt, and 5 volts, which obviously adds up to 10 amongst the 3 resistors. Mathematically, we have an equation for determining the total resistance for a bunch of resistors in series, and here it is. We're just going to add up each individual resistance. So RT is going to be the total resistance of the circuit, and then R1, R2, R3, and so on are the individual resistors. So we could have as many resistors as we want, and we would just use this equation to determine the total resistance of that circuit. So let's look for a second at a practice problem here. So we're going to take this sample circuit with 3 resistors, and we're going to determine the following things. We're going to determine the total resistance of the circuit, the current through the battery, and the voltage and current then on each individual resistor. So let's start with the total resistance of the circuit. Okay, we're going to use that equation that we just introduced on the last slide, and so that is that the total resistance is just the sum of the 3 resistors in this case. So we'll say our total resistance here is going to be 3 plus 1 plus 2, or 6 ohms. Okay. To get the current through the battery, we're going to bring back Ohm's law, and you're going to see as we're doing a lot of these problems, a lot of these circuit analysis problems, we're going to very, very frequently be using Ohm's law, often repeatedly. So I'm going to say V equals IR. And I do want to just mention real quick that this is all going to be for the total circuit. So I'm going to use the total voltage of the circuit, which is the 12 volts of the battery, and the total resistance that I just calculated, which was 6 ohms. So I'm going to say 12 equals I times 6. So my total current is going to be 2 amps. All right, so now I know the overall resistance of the circuit, I know the overall current, and when I say that, I mean the current going through the battery, and I know the overall voltage, which is this 12 volts, the voltage of the battery. From there, I can go and do the individual resistors. Okay, so I'm going to start looking at the 3 resistors I have here, and I'm just going to number them 1, 2, and 3. And I'm going to start doing my individual analysis, finding the voltage and current of each one by remembering the concept for my current, and that is that because there are no junctions or splits here, whatever current leaves the battery goes through each resistor. So because they're all in series, I know that each one of these resistors will get 2 amps of current. All right, so I'm going to put a 2 amps next to each one. For the voltage, I am going to have to do some math here. So I'm going to have to use Ohm's law for each individual resistor here to find the voltage. So for resistor 1, I'll say V equals IR. I don't know the voltage, but my current is 2 amps. The resistance is 3. So this ends up being 6 volts. So I can say the first one is 2 amps and 6 volts. For the second resistor, V equals IR once again. So my voltage is 2 amps through that one times 1 ohm. So I get 2 volts through that resistor. And then for my final one, resistor 3 here, I'm going to say V equals IR. So my voltage is going to be 2 times 2, or 4 volts. And so I can put that 4 volts down as well. And I see, if I want to just double check my math, the 6 plus the 2 plus the 4 do add up to the 12, the total voltage of the circuit. All right, we're going to do one more problem with series circuits. So I see I have another circuit here with 2 resistors in series, and this time I'm not given the same information. What I am told is the resistance of each one, and I know that 1.5 amps of current is going through that first resistor. So the first question is, what is the voltage across that 10 ohm resistor? And so for that one, I'm just going to use Ohm's law. I know the current is 1.5 amps. The resistance is 10 ohms, so my voltage is going to be 15 volts. And I'm going to go ahead and label that just because I think it's nice to have that information right there, particularly when we're doing these circuit analysis problems. So 15 volts. Next question, we want to know what is the current through and voltage across the 30 ohm resistor. And that typically is how we say that. We talk about current through a resistor and voltage across. That's just the terminology we use. My current, I know, is going to be 1.5 amps. And that's because this is a series circuit. So whatever current flows through this resistor must also flow through this one. So they will have the same current. So I can say this is 1.5 amps. And then for my voltage, I'm going to use Ohm's law once again. So as you're seeing, we are going to be using Ohm's law very, very frequently when doing these problems. And so I do that 1.5 times 30, and I get that this is 45 volts here. So I'm going to put that down as 45 volts. The last question says, what is the voltage of the battery? And for that, I'm just going to use my voltage rule and think about the one loop that we have here. And so the voltage across each individual resistor must add up to the voltage of the battery. So I'm going to say the total voltage is just going to be 15 plus 45, or 60 volts. All right, so let's switch gears here and start talking about parallel circuits. So we'll start just like we did before with the basic ideas about voltage, resistance, and current for parallel circuits. And then we'll get into some equations and practice problems. So in parallel, resistors actually combine to create less resistance, which is the opposite of what happens in series. In series, they create more resistance. And so this, in some ways, may sound a little bit counterintuitive at first. By adding resistors, we are actually reducing the total resistance of a circuit. But the way I look at it is because because the electrons don't have to go through each individual resistor, it's kind of like opening up a new lane at the grocery store. Okay, each time we add a new lane or a new register at the grocery store, it actually allows people to go out of the grocery store faster because now there's more pathways, there's more options for people. You're not going through every single register at a grocery store, just like you're not going through every single resistor for a bunch of resistors in parallel. It gives you different options. Another way of looking at it is it's like having a bunch of different routes for driving. Okay, the more routes you have, the more options you have, the less traffic there's going to be. One of the reasons why some roads get really, really backed up is there's not really a lot of other options to get from one spot to another. And so, because everyone's forced to take that one option, there's a lot of traffic. All right, that's like having a lot of resistance. If you have a lot of different options, you're going to have less traffic on each individual option because people have all those different choices. Current in a parallel circuit is going to split up. Okay, and that's because there's multiple pathways. That's because we have a bunch of different junctions here. We see where the circuit splits and then eventually comes back together. All right, so the current's going to split, but the voltage is going to be the same for each resistor. And the reason for that is each of these is on its own separate loop. So we have the inner loop, the middle loop, and the outer loop. But each loop, you only cross over one resistor. So that means that each of these resistors must have the same voltage as our battery, which is 10 volts. All right, so let's look at our equation for resistors in parallel. They obey this equation. I call it like the 1 over equation. So the way it works is 1 divided by the total resistance of the circuit of all these parallel resistors combined is going to be equal to 1 over resistance 1 plus 1 over resistance 2 plus and so on. And we can keep going for however many resistors we have. All right, so it looks similar to the series one, but with parallel, it's 1 over each one of those things. And we'll talk about a math tip in a second here for how you're going to be able to solve these. All right, so let's go through a circuit analysis here, and we'll start with the basic one like we did with the series. Same set of questions. We want to find the total resistance, current through the battery, and voltage and current for each resistor. So let's start with the total resistance. So now we're using our 1 over RT equation because these three resistors are combined in parallel. And so we're going to say 1 over RT is equal to 1 over 4 plus 1 over 5 plus 1 over 1. Okay. What I would do here, we certainly could find a least common denominator and go through all that. I would just put this into your calculator. I would actually take 1/4 plus 1/5 plus 1 over 1, which is just 1, and add them all up. And so what you end up getting when you do that is you end up getting 1.45. However, that is not our total resistance. That is equal to 1 over our total resistance. What I would do from here is there's a button on your calculator that says x to the minus 1. Okay, I always think of this as like the flipper button. It actually takes the reciprocal, but this button here, this x to the minus 1 button, will allow you to take that 1.45, all right, and raise it to the negative 1 power or find the reciprocal of it. And when we do that, we do x or 1.45 and then do x to the minus 1, raise it to the negative first power, what we end up getting is we solve for RT, and we get a value here of 0.69 ohms. You certainly are welcome to find the least common denominator using fractions. You certainly are welcome even from this step to cross multiply to get RT. So you could say 1.45 RT equals 1 and then solve for RT. But this flipper button here, this x to the minus 1, I think is a really useful trick that you may find handy in the future. All right, let's move on to part B here. For part B, we want to find the current through the battery. Okay, and so same thing we did last time. We're going to use Ohm's law, V equals IR. My voltage is 12 volts. That's going to be equal to my current times my total resistance. So again, remember we're doing all totals here. So I get that my total current, the current flowing out of the battery, is 17.4 amps. That does use the unrounded number for resistance. If you rounded some, you might get a slightly different answer, but it should be pretty close. So 17.4 amps. We're now going to go through and do the third part, which is finding the voltage and current on each individual resistor. Okay, and so to do that, I'm first going to think about my rules that I know, and I know that for a parallel circuit, they each get the full voltage of the battery. So that means that I'm going to have 12 volts here on the 4 ohm resistor. I'm going to have 12 volts on the 5 ohm resistor, and I'm going to have 12 volts on the 1 ohm resistor. Each one will get that full voltage of the battery because each one is its own separate loop. Okay, now that I have that, I can go ahead and find the current for each individual one. So I'll call this resistor 1, resistor 2, resistor 3. And so for each one, we're going to just apply Ohm's law. So we'll say V equals IR, 12 equals I times 4. And so the current through that first resistor is going to be 3 amps. Put that down there. For the second resistor, we'll say, and I'm going to skip a step here and just go right to 12 equals I times 5, but again, I'm just using Ohm's law. So we find that my current through that second one is 2.4 amps. So we can put that down as well. And then through my final resistor, and you probably don't need any math or any calculator here for this one, 12 equals I times 1. And so we get that our current here is 12 amps. All right. I do want you to notice, though, if we add up these three, so if we do 3 plus 2.4 plus 12, we get 17.4 amps, which happens to be the total current that we found using Ohm's law. And that should happen. That 17.4 splits up into 3 possible pathways as we go through the circuit. So whatever current leaves the battery, 17.4 amps, should be the sum of the currents through each of those potential pathways. Alright, so one last practice problem here. Again, this one's a little bit different than our basic one we did on the last slide. So we have 150 and 50 ohm resistor connected in parallel. We know that there's 0.2 amps of current flowing through the 150 ohm resistor, and we want to go through and do some analysis with this. So the first question is, what is the voltage across it? So of course we're going right to Ohm's law here. So the current is 0.2 amps. The resistance is 150 ohms, and so the voltage across this resistor is going to be 30 volts. All right. Moving on, we want to know the current and voltage across the 50 ohm resistor. So to start, we first know that the voltage here must be 30 volts because these two are connected in parallel, so they must have the same voltage across them. They're each on their own separate loop. And so then we can say based off of that voltage, we can solve for the current. And so we can say 30 is equal to the current times our resistance, which is 50. So when we solve for the current, we get that this is going to be 0.6 amps of current flowing through that. The last question here asks us about the voltage and current of the battery. Okay, so the voltage of the battery we know must also be 30 volts, because each of these loops must add up to the voltage of the battery. Since we only encounter one resistor on each loop, the voltage across that resistor must be the voltage of the battery itself. So because each of these is 30 volts, we must have the battery also as 30 volts. To get the current, we're just going to add up the current through each one. We know we have 0.2 amps flowing through this resistor. We have 0.6 amps flowing through this resistor. Those two come together at this junction right here. And so we can say the current is going to be the 0.2 plus the 0.6. So we get a current here of 0.8 amps.